Easy. So let's go through this, right? This is just Lenz's law. There's no calculations. So right? First, is that current? Yes, that's the current. So what's the direction? Well, the magnetic field is, I start with 0, no magnetic field here. All of a sudden I have something coming out. I don't want to change. Lenz's law say I'm going to cancel it. Induced field is into the page. Induced current is clockwise. Right? Lenz's law. So is there a force here? Yes, there's a force because if the current is here, IL cross B, the current is coming down, the magnetic field is into the page. So the current is coming down, magnetic field is, sorry, out of the page. The force is to the left. Right? We talk about using the magnet as a brake. Doesn't matter the loop is going in or leaving, the force is always restoring, trying to stop it. So the force is always this. So without doing anything, I can already tell you the force is also going to that. Is it faster? Well, because it's pushing it backward, of course it's slower, right? Okay. Now, how about here? Here, there's no more current because there's no more changes. And then, so is there a force? No current, no force. But it's a velocity still be less because I already decreased the velocity here. The velocity is not going to go back up, right? I'm sorry? Any question? Yes. Still moving. There's no current because there's no change in magnetic field, no change in magnetic flux, right? It's still traveling in here. Not when it's all the way in here, right? Like if it's going from here to here, there's no change in flux. Okay. When the loop is leaving, so now I'm used to having all this magnetic field coming out. Now I have less. Induced field is out to make up the difference. So induced current would be counterclockwise. Right? Force, yes, restoring force. And what? The velocity, of course, is less than that. Even slower, yes. Any question?
B or C is it's no. Pretty okay.
B?
This guy and this guy and this guy. Well, no, that
Constant velocity. The loop? Only initial. Okay. All right. Any questions? Yes. QV cross B is the same as IL cross B.
Yeah, but it has a velocity in the B field.
Oh, it does, but they cancel on both sides. So if I look at the loop, oh, well, actually, I have no current. Why would I have a force?
But even
Right? Even if I have a current, I will have no force. All right. Okay. So what I want to do is I want to do one more example. Actually, one small concept. I need to finish the plane wave. And then I think I'm gonna reserve half of the class for questions if you have any for the midterm. I didn't prepare any. So so now I want to look at this. Well, again, for this chapter and the next couple topics, all we're going to do is I give you a E field, you tell me the H field, I give you the H field, you tell me the E field. Because they always go together and you need to know, if you know one, can you find the other? Right, under all different circumstances. So this is one of them I want to go through. But before I do that, I want to go a little bit into the background first. So it will make it easier. Hmm? I know the midterm doesn't cover this, so I don't expect you guys really ride your bike on this topic. But I want you to remember what we are talking about here is if you have an oscillating electric field or magnetic field, as long as your circuit is an AC circuit, basically, then you have an electromagnetic wave radiating out away from your circuit, and you cannot avoid it, right? And how do we describe that? We say, well, the electric field or magnetic field, they're all traveling like a wave. So either cosine, sine, or exponential function, doesn't matter how I write it, right? Say Kc, then that means this wave is traveling to the plus C direction, the propagation, right? But in general, if you look at the slides, in general, I have this formula here, e to the j omega t minus k dot r. That's for three-dimensional wave, right? And this is only in one direction, the C direction. So what does k dot r mean? What is k? Well, k is what we call the wave vector. What is the wave vector? The direction is just give me the propagation direction. Like what direction is this signal traveling to, right? The direction on the E field is what's the direction of the electric field oscillate into, up and down, up and down. And then the wave is traveling, why the electric field is oscillating up and down. So there are two different directions, right? So the K, the wave vector, the direction is the propagation direction. The magnitude is what we call the wave number last time. Basically, if I look at if I would plot the wave, I can count how many wavelengths in that distance the wave have gone through, right? So this is your 2 pi over lambda, where lambda is a wavelength that tells you the wavelength of the oscillation, right? Are we okay so far? So K we can understand, but what is R? What does this R mean? What is R? Well, R is the position vector. That means if I want to look at a point over there, I give it an R direction, or R coordinate, then you can tell me what's the wave at that point, right? So for example, if I look at my one dimension wave equations here, what does the K and Z and omega and T tells me? Omega tells me the oscillating frequency, right? It's 2 pi f. Time is at any specific time and any specific location, you can tell me what's the magnitude of this electric field, direction and magnitude, right? Are you with me? So if this is an electric field, that's what we get. If we are looking at the sound wave, I give you the time and position, then you can tell me what's the pressure of the air pressure at that instant, at that moment, at that location, right? If this is the tidal wave, then you can tell me what's the water displacement, the height of the water at any specific time, at any specific location. So this is a specific location, and this is a specific time, right? So in other words, R is my position vector, which is my x hat, y hat, z hat, or xyz in the Cartesian coordinate. So far, so good? Okay. All right. So what is k dot r though? Let's take a look. What does K dot R mean? K in general is a vector. It can have X component, Y component, Z components, right? So I'm going to call KX, KY, KC, right? Just in general, right? Any vector. Some of them can be zero, but in general, it's three components. And then I have the R vector, the position vector, which is X, X hat, Y, Y hat, Z hat, right? So when I take the dot product, what do I have? X hat plus KY, Y hat plus KC, C hat. That is my K dot R. Oh, sorry, no hat. I'm ahead of myself. Thinking of something else. K is not the velocity. It's called a wave vector. The direction give me the propagation direction where the signal is traveling to. The magnitude tell me what is the wavelength, 2 pi over lambda. But what is K vector? We say K vector is X, KY, KC components, right? So if I want to write it in the vector form, this is what it looks like, right? Any vector, X components times X hat, Y components times Y hat, and so on. But when you look at this, what can you tell me? They look exactly the same except one with the hat, the other one without the hat, right? So, in other words, if I look at the wave formula, I can tell you what is a K vector is. So let's go back to our old example. Let me just make one up. So for example, if I have my electric field is whatever, 10 cosine 100t minus 30x, right? Let's say this is my electric field. What is the direction of propagation? Tell me. Positive x, right? Okay. What is the K value? Right? In other words, the K vector is just 30x hat, which is just the negative of this number. Are you with me? So when I look at this form, automatically I look at this, I say, well, K is just equal to, this is negative, I change it to positive, and I see X, I put a hat on it. Are you with me? If you understand this, this is very easy. The rest are very easy. Let me do one more time. Position X. Yes. 1/meter. X, because it's linear along the X direction only. It does not depend on Y and Z. So I only, it's a plane wave. So every point with the same X, they have the same magnitude. Well, anything in the cosine is phase, right? Angle is a phase. Yeah.
When you have an expression with this, right, that's the result of K dot R.
Yes,
It's basically just K.
right.
So where on
Becomes X without the hat. K is, so the question is, well, this is K dot R. So if I read the K of this, what happened to the R? Is in here without the hat. So what we're saying is, look, what is K here? I say K is equal to 30x, right? So what is K dot R? Work with me. 30x, no Y, no z, that onto x, y, z. What do I get? 30x.
So what does that actually mean? Then you're only looking at the field on the x-axis? Like, are you only, this is the point where the R is like where you're observing it versus where it's propagated.
That means any point has the same x, it's the whole plane. Doesn't matter what y and z are, as long as along the x-axis is the same x, the whole plane has the same electric field. Plane wave, that's why we call it plane wave, right?
So x equals 0, then the E field is cosine of E
That's right,
1.
right,
That's
right. So that would be the phase shift of different location, of different phase. Yeah. Right? Okay, I know wave is a kind of a abstract concept, but not for double E though. You guys use it all the time. Right? All right. So let's do one more. So having said that, that means if I see something like this, what is my K vector? To look at this, remember to change the sign, right? The positive becomes negative, negative becomes positive, and put a hat on all the x, y, z. So this is minus 30x hat plus 40z hat. Okay. Make sure you know when to put the hat, when not to put the hat. It makes a huge difference. The meaning is totally different.
Then on this point, that E field is the same, no matter what point on that.
On the y. Right. So far, so good. I know we probably have to go through this again after the midterm. Yeah. All right. So now we're ready. Also, that's one thing. The other thing is this. Let's go back to this example. We say by looking at this type of expressions, we can tell a lot about this wave, right? We know it's a wave, we know the direction it's traveling to, we know the frequency is oscillating, we know the wavelength, right? And with knowing that too, that means we know the velocity. Well, how do we find the velocity again? Velocity of a wave is frequency times lambda or omega over k. What is omega? Whatever in front of the t, that's omega. What is k? Whatever in front of the x, y, z, that's my k. So in this case, the velocity is 100 divided by 30, which is equal to 3.33 meter per second. Right? Okay. Now, when you see an expression like this, you don't have to ask me, is this propagating in vacuum? Is that propagating in air? Or what is it propagating in onto or into? Okay. You don't have to ask me because you can calculate it. If this is a vacuum, then the velocity would be speed of light, 3 times 10 to the 8. Because this is not speed of light, so you know it's not in vacuum. Right? Okay. So how do I find the medium then? Let's go back to our definition again. The first definition is velocity. Velocity is defined by mu over the square root of mu times epsilon. What is mu? Mu is permeability in free space times the relative permeability epsilon is epsilon in free space times the epsilon, the relative epsilon permittivity, the dielectric constant, right? Right? So if I rewrite it, this is 1 over mu naught epsilon naught times 1 over mu r epsilon r, right? What is 1 over mu naught, square root of mu naught over epsilon naught? This is just the speed of light, right? So this is speed of light divided by, now, for all the cases that we deal with, like we're thinking of the wave, the cell phone tower is sending me a signal, but the signal is propagating in air, or I want to do a submarine communication, the signal is traveling in water, or my PC board, on my circuit board, right? So none of those are magnetic material, right? So for all the cases we deal with, other than the boundary condition problem, we are always dealing with non-magnetic material. That means you cannot stick a magnet to it and attach to it. Always. So that means mu r is always equal to 1, unless we specify it, which we never do. So this is just defined by this. Okay? No questions so far. Then I'm going to bring you back to physics 52, optics. When you're learning optics, what did you learn? There's something called the index of reflections, right? What is that? What does it tell me? It tells me how much would the light bend in the material, right? Because it bend, it refract. So how do I define this? This is the ratio of the speed of light divided by the velocity of the light in the medium. This is how it's defined, right? The ratio of C and V. But look at here, V is equal to C over the square root of dielectric constants. So what does that mean? That means index of reflection for non-magnetic material, which again is all we're dealing with, is just equal to my square root of the dielectric constant. Right? So this relation is very useful. And the reason this is super useful is if you understand these relations, you don't always have to go to what is mu naught, 4 pi times 10 to the minus 7. What is epsilon naught, 8.84 times 10 to the minus 4. You don't need to do all that because all you have to do is work with speed of light or work with eta naught. Do you remember what eta naught is? The wave impedance when the wave is traveling in vacuum. What's that number I asked you to remember? Remember this. You will thank me later. Right? The wave traveling in air, 377 ohms. So how does that relate to this? What is eta again? Well, eta is defined as the ratio of the mu over epsilon, right? Again, what is mu? Mu is mu naught times mu r. Epsilon is epsilon naught times epsilon r. We say we always deal with non-magnetic materials, so mu r is always equal to 1. And then I have this square root of mu naught over epsilon naught. What is that equal to? This is just my 377 ohm. The wave impedance is just equal to 377 divided by the index of reflection. What is the index of reflection? Square root epsilon r. How do I get that? By looking at the ratio of the velocity. Are you with me? If you are, we are ready to do the example. Any questions? Okay, now we are ready. We'll get rid of, okay. So let's look at this example. Now I'll give you a E field, non-magnetic material. I want you to find H, right? So it's non-magnetic always. Find H. So what do? Well, first of all, I'm going to use the three rules. So I'm write H is equal to some kind of direction and magnitude, which I'm going to find out later. I'm just going to copy the phase part, the wave part here. Whatever I have on the E, I'm just going to copy this, right? That should be easy one. And then change the unit to per meter instead of volt per meter, right? You should at least get 1 point on this. And then I need to figure out the direction and need to figure out the magnitude, right? The direction, I know E equals H is K, the direction. So how do I find K? Looking at this, what is K? What is K vector? Tell me. Negative. Okay, not right on here. Huh. Negative 3c hat. Don't forget the hat. Right here. I don't need to write. Right? That's the first step. You need to be able to read this off from here. And then once you have this, I'm going to draw it. So I see a Y and Z, so I'm just going to call one is Y, one is Z. Again, doesn't matter which one is Y, which one is Z. But once you draw this axis, then you should find out where's the third one. So where's my X? Positive X. Is X in or out? Anybody? Is X in or out? This is my Y. This is my Z. Where's my X? In, right? Okay, so X is in. And then, what else? So E has the direction of X. So that means E is going into the page, right? And K is -3 hat, so it's -3 units here, and 1 unit along the C, so it's 3:1 ratio. That's my K. Right? Yes. Because Y is X into the page, because this is Y, this is Z. X, Y, Z is the right hand rule. So if I say X is the finger, Y is the palm, Z is my thumb. Z is my thumb. X is my finger, Y is the palm facing up, with my fingers pointing into the page. Right? So X is into space. X, Y, Z. X, Y, Z. Right? Okay. So now E is into the page. K is in the second quadrant. Where's my H? E equals H is K. So E is into the page. That's my finger. K is the thumb. So I line them up. Where's my palm facing to? In the third quadrant. Right? Okay. So how do I express this direction though? Well, K is 3:1 ratio on the C and the Y. Then that means H is 1:3 ratio. Right? 1 on the X, 1 on the C, 3 on the Y. They both are negative because they both are pointing down. Ah. Any question? So I know this is 3 unit down minus y, 1 unit to minus z direction. And normalize it, take a square root of 3 squared plus 1 squared, so square root 10. Right? Okay. So I'm just going to leave it there. Any questions so far? All right. So what's left? The magnitude. E naught over H naught is eta. But what is eta? Is eta 377? It did not say it's in vacuum. In fact, if I give you both frequency and wavelength, most likely it will not be in vacuum, because I would have to do extra work to check and make sure it's in vacuum, right? I don't like to do extra work. So if you see this, both numbers are there, you can pretty much bet on it's not in vacuum. So how do I find it? Well, I know velocity is omega over k. What is omega?
10%.
10 to the a, whatever in front of the t, right? So that's 10 to the a. What is k? The magnitude of this, square root of 10. Right? K vector is this. What's the magnitude of this vector? Square root of 3 squared plus 1 squared. Right? That's velocity. Okay. What is the dielectric constant or index of reflections? Well, we say C over the velocity is my index of reflections. So if I want to find index of reflections, that would be 3 times 10 to the 8 divided by this velocity, 10 to the 8 times square root 10. 3 times square root 10. Right? So now I can find eta. How do I find eta? Eta is equal to eta naught divided by n. Eta naught is 377 divided by 3 square root 10. But eta is E naught over H naught, so what is H naught? H naught is E naught over eta. What is E naught? Okay, not erase it. Okay. 20, right? E naught is 20. So it's 20 divided by 377 times 3 square root 10. So altogether, what do I have? Altogether, what do I have? I have H field is equal to, the direction is minus 3y hat minus c hat divided by square root 10. The magnitude is this, 60 times square root 10 divided by 377. The square root 10 always cancel, that's why I don't multiply out. And then cosine of blah, 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 whatever I have here. M per meter, right? That's it. I mean, you need to simplify it. Don't make me do arithmetic. I'll take points off for it if you do. Okay. Any questions? So when you go home after the midterm, make sure you redo these examples, right? Again, the very first step of your studies should be go over do all these examples we did in class. And if you don't understand it, ask me on this example. If you understand it, then move ahead and do your homework, right? You have to do this step. Any questions? We cover a lot. How do you find the K? How do you read it off? How do you find the materials, dielectric constant, index of reflections, and all that? Right? So we are pretty much done with this chapter. there are more topics to this chapter. I separate them into different chapters in my book. Polarization, lossy medium, those are all plane wave problems. Those are all in the book, in your textbook too. Okay.
Well, if the, we, no, if we times y, and how do you put that apart?
3c times what?
Times y.
Times y? Oh, then you cannot do that. Like this. It's not,
Yeah.
it's not linear. No. Mm-mm. So we can talk a little bit more after the midterm. One question would be, how do you know this is a wave or what kind of wave this is? So when you are taking learning wave at the beginning, back in physics time, there's something called standing wave. There's something called traveling wave, right? What's the difference? What is a standing wave? Does that satisfy the same wave equations? How does the wave function look like? Anyway, we'll talk about that next time. So now, unless you don't have questions on the second midterm, I'm going to open up the floor for any questions you want to ask on the midterm. If you have no questions, then we'll come back to this. Yes. If it's in chapter 6, yes. Like what?
Like finding charge density based on current density. Observation of charge density.
So just in general, right? Let me repeat that again. The topics that I feel like you should know, you really should learn, are the ones that I usually cover in class. If I don't cover that anything, like I never talk about vector A, like the vector potential, you can pretty much skip those in the homework. I'm not going to ask you that in the exam. Because if I don't feel it's important, I will not ask you that, right? If I feel it's important, I would have at least talked about it in the lecture. Right? I'm not saying it's not important, just like I don't have, it's not high on the priority. I have so many things to cover. Any questions? No, sounds like you want to do the wave again, huh?
You said it's covered.
No 4, just 5 and 6. All magnetisms and Faraday's law.
Fancy.
No, the textbook. So again, the rule is I'm supposed to pick problems from the assigned homework, but I can modify. But to what extent I can modify it, that wasn't specified. So you can pretty much bet on I would modify to closer to what we did as in examples in class. Right? So for example, in the last exam, I don't know if we do that. So I talk about image charge, like a line charge and image charge, how to refine the E field and potential. And then we did a point charge on the ground plane. And then homework, there's a point charge on the ground plane, but there's no line charge on the ground plane, I don't think, right? So I just change that problem if I want to, change that point charge to a line. So I only changed a little bit in the homework, but it's a totally different problem, right? So
Briefly.
3 questions. At least one would be Faraday's law for sure. Yes.
Go. I did with the. With the image finding, but with the.
6.16.
Yeah.
Which homework set was that on? Number, yes, what about it?
I would,
So we have a semi-infinite wire. Put it on the ground plane. So when I see the ground plane, I think of image current. So I remove this ground plane, then this would have an image current to minus infinity. What's the direction of the current? It's perpendicular, so they're going in the same direction. In other words, I can replace all this with just infinite current in front of one ground plane. Now I want to remove this ground plane, this infinite wire, create an image infinite wire on the other side. So now I'm really looking at two current. If I rotate the drawing, like this one's going up and down, this one is going in and out of the page from minus infinity to infinity and so on. So on the right, the current is coming out. On the left, the current is going in into the page, looking from the top, right? So you understand my, okay. So this was used to be the ground plane, now I remove it. So now I want to find the magnetic field due to these two wires. So at any point x, y, z, so I'm just going to pick one point. And of course, to make my life easier, I'm going to pick a positive x and positive z. I mean, you could do that here too, but then you have to make sure you check the coordinate, would that work when z is positive or negative and all that. So to make your life easier, I always pick one point that's not too close to the boundary, far away. I don't have to worry about plus and minus and all that. Okay. But you should always have a habit to check your answers. I mean, right? Like, does it work? Yes.
6.1,
Huh?
6.18, I think. On that homework.
6.18?
Yeah, I think it's the problem.
The
with it.
next problem.
Oh, it's not this problem?
Yeah. Just the setup as well.
Oh, you mean after this one?
Yeah.
You want to, okay. So let's kind of go through this one, right? So far so good. The parts that everybody misses, you are so focused on the R vector, you keep forgetting the magnetic field is always perpendicular to the R. So if I'm looking at the current coming out here, the magnetic field is going into these directions, right? We say the magnetic field is going around, but what does that mean by going around? That means if this is my center of a circle, I'm going to draw a circle with that radius, and the magnetic field is always going around. But what does that mean by going around? That means at any point is going tangential to the circle. So at this point, the magnetic field is going here. At this point, it's going here. At this point, it's always tangent to the circle. That's what the phi hat means. The phi hat is not a fixed location in your Cartesian coordinate. It's only fixed in your cylindrical coordinate. Yes. Could be anywhere, but again, if you want to create less work for yourself, always pick something positive. Like pick something in positive x, positive z. I will not pick a point here, for example. I cannot pick a point here either because these are in the ground. I cannot calculate anything in the ground, right? Okay. So once you have that, then to write the magnetic field, that becomes a relatively easy task. You know, the magnitude is mu naught I over 2 pi r. This is from an infinite wire. And then the direction, looking at the graph, you have to draw it. I mean, I'm seeing a lot of people doing homework or doing problem without drawing it. I don't know how you can figure out the direction without drawing your theta on your diagram, right? Because you're supposed to read it off from the diagram. So I draw this and I'm going to label this. I'm going to call this theta 1. that means this angle is theta 1, right? So if this is my theta 1, cosine is pointing up, that's my minus c. Sine is pointing to the right, that is my positive x. So that means sine of theta is my x, and then no y components, and the c is negative cosine theta. And then you go back to this triangle. Go back to this triangle and then say, okay, I know this is theta. What is sine theta? Well, is this over my r? What is this? This is my z. So this is my z over r1. What's my cosine? Is this? What is this? Well, here is x. Here is d. So this is x minus d. Right, and so on. So once you have the first one, the next one will be easy. You say, oh, the other one is this one, the vertical components is still c. And then my x components, instead of this little distance, now is this big distance. Now it's x plus d. And then my current is the opposite direction, so I'll put a negative here. So this is my B1, B2, and then just add it together. Once you write the first one, everything follows. Again, the most difficult part, the part that most students make mistake was at the beginning. You don't seems to know where to find or where to draw the B1. But again, if you don't know how to draw it, there's no way you know how to write it correctly. Don't try to remember the solution. It will never work. It's not really very complicated. You just need to, if you are stuck in this little thing, just make sure you unstuck it. Ask questions. I have so many TAs for you to ask, right? And in the weekend, if you are studying in the weekend, if you have questions, put it on Discord. Someone's going to answer it. I will try to answer it right away. Or if I need to hop on to Zoom with you for a few minutes, let's do that, right? I'm busy on Sunday, but I'm open on Saturday or Sunday evening, late evening. I'm okay too. I don't sleep until very late. How late? 2 o'clock? Well, I mean, I have a lot of years of schooling. I've been trained well. You guys don't go to bed early either, do you? Yeah, that's what you're supposed to do, right? All right. Any other question on this? If not, then I'm going to move on. Right. Read this solution. Even though you say, oh, I don't need the extra credit, I'm not going to do any extra credit. You might want to browse through this, right? Because the exam problem is not going to be exactly like your homework problem. I would change it so it would be more like my homework problem, right? Guarantee you. Right? So the next one, the next one is slightly different because now the current is in and out of the page. It's already an infinite wire in and out of the page. And then I put it in front of the corner. So each wire, this wire is going to create an image to this side. This is coming, current is coming out, so the current is going in. And then I remove this ground plane, right? And then everything flipped to the other side. This current going in becomes the image coming out. This current coming out means the image going in. So now it's a 4-wire problem, not 2. And then you pick a point again, pick a point along the positive x, positive y as far away as possible, like right here. And then you draw the first one. All you have to do is draw the first one. So what's the first one? Do it again. Right? The current is coming out. That means the magnetic field is going around a circle. Again, what does that mean, going around a circle? That means at this point, the magnetic field is tangent to the circle. That means this is perpendicular. That's what the phi hat means, right? If you don't understand it, you guys have to ask. Don't assume. Okay. All right, so once you have that, then you just pick an angle. In this case, I pick this angle is theta. Then that means this angle is theta. That means this angle is theta. Once I have a theta, I can find the direction of B1. So what is B1? Mu naught I over 2 pi R1. And then the direction is cosine is going up is the Y. So cosine theta is the Y. Yes, sine is going to the left is minus X. So it's minus X. And then 0. That's it. And then you go to this triangle. And then you say, well, what is cosine? It's this little distance. What is that little distance again? It's the whole thing X minus this S. So cosine is X minus S over R1. Sine is this. What is this? The whole thing is Y minus D. Once you have the first one, you can figure out the rest, right? So you have B1, B2, B3, B4, 4 wire, 1 wire, and 3 images, right? Good.
I have a question for.
5, 12.
The,
5.
Five.
My problem. Okay. That's homework 7. Oh, I'm not going to talk about that. 9. Oh, don't. What was the question?
So basically,
Okay, hold on a second. Hey, I did not. Oh. Do I have one before that? Did I attach the homework at all? Oh, the textbook, the text. Okay. Okay, 5 what? 12. Okay, what's the question?
so. How
You could, but why?
just go down.
But why?
Should be able to.
You should be able to, but why?
Because
I try to avoid it because I don't want to make you confused. Right? Why, if you can do it in one recipe, one concept, why do you have to separate into emotional EM, right? But if you want to, okay, fine. So you want to say, I want to find this EMF from this. DL, and it's closed loop. Okay, then you just do all 4 wire. The velocity is this velocity, right? And the B is given. So dot DL is this DL, and then this DL, this DL, and this DL.
be
Yeah. Right.
Three centimeter.
To 3 centimeter, but X is equal to 0. So you substitute X is equal to 0 here. Right? Here, X is equal to 2 centimeter, 0.02. So you substitute X is equal to 0.02 here. Right? Velocity is all the wire has the same velocity. So you can do the V cross B first.
I guess my point is rather do scoring. The tool was.
Yes. V cross B would be in or out, in and out of the page from the top. And when you dock onto DL, that's when you get zero. If you think so. By all means. How you do your math, I don't really care, but I think what I have told you to do is a lot easier and simpler. I don't have to worry about, do I use that, or do I use dBdt, or do I use... Just find the flux, take a time derivative. Right? You don't even have to think. How nice for a change. Yes,
So that it's homework with due on 4:30.
you can do it. You can turn it in tonight. Is that good? Before midnight, okay? You need more time? You should. Whenever you can turn it in, and you can get at least partial credit. Right? So the rule is, if I'm grading it, as long as you turn it in before I grade it, I usually don't take any penalty. But I might grade it tonight. So, yeah. I'm sorry? Regular homework. No, because once I release the solution, I just don't do it. Now, starting this week, I actually have TA to grade the homework, so I don't even know when he is going to do that. Okay. Any other questions? You feel like you're prepared? You feel like it's easier, better? No, no change of flux, no EMF. And the flux is, so a lot of times we say, okay, you flip the switch, you turn it on, you see an induced current. That induced current doesn't last very long. It's only that instant because the current is going to dissipate as heat. How fast? Well, that's the time constant of the circuit. Typically, it's microseconds, nanosecond range. So it's like split second, a spike, and then unless you keep changing, right? Yeah.
So in like every single one of these problems, there's always like a cosine or a sine. And then
Yes.
take the derivative and one of the two sides of the product rules goes away at time equals 0.
Yes.
But what if you have like a
Sine and sine.
how do you tell which one's dominant?
So if one is exponential, what is the other one? Exponential when t is 0 is still 0. It's still 1. E to the 0 is 1. So that's like a cosine, right?
They'll both have an have the thing in front of you.
You have to look at the function, right? Which one is bigger? Right? Yeah.
But it won't always be 0. Yes. Like it won't always be convenient that one.
But it's not always competing either. You can have two cosine functions. They both give you counterclockwise. So it doesn't matter which one dominates, still
It's
counterclockwise.
only if they're fighting.
Yeah, as long as you have one sine, one cosine, one is plus, one is minus, they're competing. That's the time you need to figure out which one dominate and what the current be at T0. Yes, so you look at the term and say the cosine term dominate. Where does that term come from? What derivative am I taking? Am I taking the derivative of the oscillation of the field? Am I taking the derivative of the moving
I want
loop? That tells me what is dominate. Make sure you understand Lance's law because those are the easy point, right? Supposed to be.
is that
I'll see what you get on the quiz. Those are supposed to be easier point. That's right.